everyone. Hopefully everyone has learned something new or several things new. And hopefully it was a little bit, there are many other, so until now I really covered kind of everything that I wanted to cover, which is, the kind of the fundamentals of AI, just to put things in perspective, then a little bit fundamentals of AI hardware, and the assignments kind of reflected that. And then yesterday we talked about TinyML, so we went from large accelerators to small accelerators, and now there are many other things that could be done, but I thought today to again, based on some discussions that I had with the students, to go in the sorry, I have a little bit of a rough breathing. Sorry. Yeah, maybe some water. Yeah. So to go in the direction of, breaking the memory wall in the direction of processing in memory. So we'll have two different kind of approaches to processing in memory, and one of them is going to be more analog. And another reason for having this lecture is that until now we kind of we're a little bit too digital everywhere, and I know there are several, if not many, kind of analog designers in the audience, and then because it's kind of fun to talk about this. So like you saw, I like to do with with my presentations. Give me one second. I like to put things in perspective. So to give a historical perspective on how we got where we are, and one lesson probably that everyone should take from this is that it's really, really hard to come up with completely new ideas. So even ideas that seem very fresh and very new, if you look, back in time, you will discover that, they've been looked at before. And it's kind of the same with some of these, approaches for AI hardware. But in general, actually, analog computers in many ways, predated digital computers. And, the idea with those, and this I'm talking now many decades ago, 50, 60 years ago when these were first proposed. And they were also proposed in the context of, military applications, World War II. And, with a digital computer, in order to calculate the things that the military were very interested in, trajectories of things that you shoot, to the enemy to make sure that you hit the target. With digital computers, you do those computations by, taking typically a differential equation and then, doing a numerical, digital numerical analysis. You discretize it in time, and you basically compute those equations with, again, multiply and add and things like that. Now, with analog computers, it was a very different approach in the sense that with analog computers, there was this attempt to recreate the differential equations with analog components, with op amps, capacitors, inductors, and that when you have an analog circuit with such components, you end up with some kind of differential equation that represents the relationship between currents and voltages, and and if you build an analog circuit, you can build it in such a way that the form of the differential equation looks exactly like the differential equation for the physical phenomenon, the kind of the projectile flowing. And then you can solve, basically you measure, the solution to your problem is measuring a voltage or measuring a current, and that's going to give you, maybe the distance and, the coordinates of the target and things like that. So, this is basically, a very different way of thinking about computing, and in some sense is not computing. Because you are just mimicking the one physical phenomenon with another physical phenomenon that's electrical now, and you measure this one, and you can figure out what would be the and this is in some sense nowadays there is a buzzword, I'm sure you've heard it, digital twin. So there is a big effort everywhere in the industry to create a digital twin of, again, a physical thing. So for example, when you have, in our field, a foundry that makes chips, it's so expensive and complicated to experiment. So in the old days, basically, or in the clean room, the way people that are doing kind of fabrication and devices, that you can try. You put a little bit more doping, a little bit, more whatever temperature you increase and things like that. So you can try different things in order to improve your process. But that becomes very expensive and complicated for modern, nanometer scale processes, because again, there are very many steps. They are all very expensive. So there isn't a big, all the companies are doing. They are creating a model of the process, and you do all these experiments instead of doing them in the physical domain on the wafers, in the clean room. You do them in this kind of digital simulated environment, and that's called the digital twin. And there are, many other, digital twins for airplanes, digital twins for, in some sense, that's exactly what was done here. This was an analog twin of, a physical process. And again, you see there is a whole list of things that they've done with this, dams, electrical grids, irrigation projects, weather, again, and final comment, and I'm spending 20 minutes on one slide at this rate. Tomorrow we'll finish this lecture. It's very interesting that now there is also a big buzz about quantum computing. So that quantum computing is big time in the news, and I would say that one thing about quantum computing that still needs to happen. So we still need to build the quantum computers that are large enough and have enough qubits and all that. But frankly, another thing that's, I think, in some sense missing is a killer app. I'm not sure that right now, there is a killer app breaking crypto, but that's really a real killer app. It's a bad thing, because, we'll have to invest a lot of money in post-quantum, cryptography and things like that. But at this point, there is really not necessarily a very important quantum application where quantum would make a a huge impact. But when Feynman, Richard Feynman, you may have heard of Richard Feynman. So he was a famous physicist. He was actually involved in World War II with, the first atomic bomb. But he proposed this idea of, actually, he proposed many ideas that, were very influential in our field. So he proposed quantum computers. He also proposed nanoelectronics. So he was the first one that says, actually, it's a famous quote from him, there's a lot of room at the bottom. So basically, going into the nano. But in quantum, he proposed quantum computers, but not the way we think now about quantum computers. In other words, now I had some discussions with students, now many people think about quantum computers as some kind of a replacement of a digital computer. It basically in that role, Feynman was interested in quantum computers to solve quantum problems. So basically, quantum, Schrodinger's equation is very complicated and it's very hard to solve numerically. And it's very hard to do anything there are some analytical solutions, but, it's a really hard problem to solve these quantum problems numerically, on computers. On the other hand, if you have a quantum computer, because the quantum computer, has quantum things going on, it's a little bit like this idea. So you can have a quantum computer in which you can simulate quantum phenomena intrinsically because they are already quantum. Okay, so any questions about this long introduction? Yes?
Is there any quantum exist or like a digital
one? Can you ask again? I didn't understand the question.
Yeah. Twin or digital twin. Is there any quantum twin exist or just?
Well, what I'm telling you is that Feynman, when he proposed the concept of quantum computer, was exactly as a quantum twin. I don't think right now there is any effort in that direction because the people that build, it's really the people that are building quantum computers are the people that also build digital computers right now. So Google, IBM, all these companies. So no, as far as I know, there is no effort right now to build a quantum twin the way Feynman was envisioning it, and and also which is very similar to this. This is not a thing anymore. I mean, as far as I know, there is no company right now that's trying to, to do this kind of thing, to create an analog computer where you mimic a physical phenomenon kind of. So no, as far as I know, no. But if and when quantum computers become reality, I assume that there are going to be some people that maybe they will resurrect this idea for quantum. Okay. So again, and you can see this is before digital computers, 20s and 30s, 20s and 30s. Differential equations, how I kind of already said everything about this. There was an actual differential analyzer in 42. And you can see some metrics. We talked about metrics. So 100 tons, 2,000 vacuum tubes, and 150 motors. I don't know what the motors were doing, but and it was kind of a secret project during World War II. And yeah, after the World War II, basically it was replaced by by the first digital computers. And yeah, these are some photos. You can see how they look like. And yeah, so there are, there are some advantages. It's a very simple idea. You just set it up, energy efficient. You represent values with continuous values. They are inherently parallel. It's a circuit. There is no Amdahl's law. There is no memory. Yeah, so if you can describe a problem as a differential equation, and many are like that, and there are some, yeah, this is an interesting place where analog computing and quantum computing, actually, there is a little bit of an intersection there. And again, those of you that are there, it seems that there are a few people fascinated by quantum computers. You will see that some people, and you can Google, quantum Ising machines. You'll see that there are some claims from people, and there is actually, Nikhil Shukla, that Professor Ambika knows, works exactly in this at our university in this direction. You can create kind of analog computers, so to speak. There are these oscillators, coupled oscillators, and interestingly, they can solve kind of similar combinatorial problems like quantum computers can do, and they are also quite efficient. And there is this claim that they are competing. I'm not sure. Again, maybe it's an over claim. So there are many disadvantages, though, and that's why we don't do any. And the fundamental. By the way, if no one told you this, the fundamental advantage of digital circuits compared to analog circuits, and the reason digital has taken over the world, is one thing, and that is the regenerative property of digital circuits. Basically, you have an inverter, and you have an input and an output, and you have noise on the input. If that noise is not large, if it's smaller than some threshold, at the output it disappears. That's it. That's the big advantage. And that really, and analog circuits don't have that. If you have noise at the input, you have it at the output, and then it keeps going. So, and those of us that are old enough to remember analog TVs and analog radio and analog photos and analog this and that, that the quality was much worse than it's now with digital. So, but anyhow, so that's fundamentally the biggest problem. And there are this limited precision. You cannot really do very precise computations. You don't have memory. I mean, that's an advantage. You don't have a memory wall, but then it's kind of hard. The results kind of disappear. It's not general. I mean, as long as you can map the function to that will work, but otherwise it doesn't. A digital computer is very versatile. You can do anything on it. Yeah, so there are many limitations, but there could still be very special, precise problems where you could use something like this, and this is an example of yeah, I'm going to move because this is just history, but basically you can start with a differential equation, and you rearrange it, and then your computer program looks like these blocks, and the way the analog computer looked like, it would have these building blocks, and then the programming would be connecting with wires, literally plugging in wires to create this circuit on the outside. And there are all kinds of scaling things. I mean, it becomes quickly very annoying. And this is a modern analog computer where people, I would say, for fun, created this, and probably you can Google it, the analog thing. And you have you can adjust values on the inputs by hand, and you can create circuits with these wires on top, and then, your result, comes at some point on the output. Now, this is an example, and I think Professor Ambika a couple of days ago talked about thermal effects in integrated circuits. And, computing the temperature profile on a chip, requires a temperature model. You need the power inputs from the circuit that dissipates power, and then you have the model. And actually, in my group with my collaborator, Kevin Scadron, we've been working on this problem for, 20 plus years. We got the Best Paper Award in 2003 for kind of introducing this problem to the, at the time, the kind of the computer architecture world, and, they were not really looking at thermal as something that they should care about. At the time, chip designers were doing their chips, and then they would send it to, to the packaging people to, solve the problem of, removing the heat and all that. And, that was perfectly fine in the old days where the chips were relatively small and the power numbers were not that high. So, temperatures used to be quite uniform and not that large. And, so the packaging people would just deal with it. If it was 1 watt, they would do one package. If it was 3 watts, they would do another package, and it would just work. Once chips have become really large and the powers have become, hundreds of watts, and you have these localized effects, then the designers need to be aware of it and, do something because, they cannot just pass it to the packaging people. And, we came up with a tool called Hotspot. Maybe some of you that are doing thermal work are using it. It's still widely used in the community. But again, someone has come up with an analog computer basically doing thermal. So, this is exactly the circuit that we are using to model thermal. It's basically a resistive grid. It's a two-dimensional resistive grid. These, the resistances, are, you can call it a twin of the chip's thermal resistance, of the silicon thermal resistance. And when you apply, different currents, so in a thermal circuit, you have the analogies to an electrical circuit. So turns out that power is equivalent to current in an electrical circuit. And you have thermal resistances, which are equivalent to electrical resistances, and then temperatures are equivalent to voltages. So basically, if there is a power going into a resistor by Ohm's law, by thermal Ohm's law, the temperature, which is the voltage, will tell you what the voltage is. So here, you can kind of apply these currents, and so this is the actual circuit. And there are also capacitors, and the capacitors are the specific heat of that material. So temperature has this spatial distribution, but there is also a temporal. So when you apply power, the temperature doesn't go immediately. It will go high with some kind of a profile. Okay. So now we are finally at AI. So that was an introduction to kind of bring everyone up to speed with analog computation. In many ways, it's the analog twin that World War II people, or before World War II, they were doing, because you basically take an equation, and the equation is Mach. So you multiply and add, and you map it to an electrical circuit. And the electrical circuit is this one, very simple. Basically, an array of resistors. So you have voltages, the resistors have conductances, and the value of the current that flows to the resistor is voltage times conductance. So you have, and basically this is Ohm's law. And so you have the multiply here. If your conductance is the weight and your voltage is the input of a MAC, and then you have all these currents together on. So, you can think of this as the word line and the bit line of, of a resistive RAM. On the bit line, the currents add up with Kirchhoff's current law, and that gives you the add. So you get multiply and add by this very simple circuit, resistors and wires, that's it. So yeah, and in terms of the data flows that we talked about, remember we talked about, weight stationary, output stationary. Such an approach is basically what you would call a weight stationary, because you program the resistors with the values of the weights, and then you can apply arbitrary inputs in different stages, and you keep reusing the values of the weights. So any questions about this? Yeah, I mean, yeah.
Why does the accuracy of this is much lesser compared to digital? Is it because of the tolerances of those resistors or the noise that is basically added?
Yeah, because of everything. And again, it has to do with the regenerative property. So in many ways, this is equivalent to just one. So if you have a digital computation, you may have 16 bits or 32 bits. And the precision doesn't come from each bit. It comes from the fact that you have multiple bits. And each of the bits regenerates each of the bits can be very flaky in terms of precision because, it's just one bit, just one threshold. So if it's below the threshold, it's 0. If it's above the threshold, it's 1. Here, all the computation is just in one wire. So yes, noise, nonlinearities, temperature, everything affects the value. Ironically, an analog value, you can think of it as almost infinite precision because, it's basically a continuous value. So it can be any real number. But because, all these things, it's never, it's going to fluctuate in time, in space, from chip to chip. So you can never get more than 3-4 bits of precision because of that. So it's the signal to noise ratio, all these things. So yeah, it's an interesting, and frankly, maybe I shouldn't say this, I know you are recording and this is maybe going to go on YouTube. But that's exactly a reason why I'm a little bit a skeptic on quantum computing. Because quantum computing inherently is an analog computer, so the quantum, value that's there, it's an analog value. And of course, in quantum computing, in order for it to work at all, you have to have, zero noise, that's why they work at, cryogenic temperatures and all that. But ultimately, it's still an analog value. And, the whole premise of quantum computing is that that value is exactly the one that, you would get when, when you solve the Schrodinger's equation, with kind of infinite precision. So I'm not sure how that's going to work even for quantum computers in practice. The fact that, you need that value to have fundamentally infinite precision. I'm not sure how that, but definitely here it doesn't work. Yeah. Which, well, okay. So these are very, yes. So these are very, well, so in the previous slide here, you are trying to mimic, a physical, a chip. Basically, you are trying to mimic a chip. And the chip has capacitors, has resistors. Actually, you need to pick the values. So, it's like the analog twin. So you need to pick the values that you would get from about extracting parameters from, when you design a chip and then you extract parameters, parasitics, this. In some sense, these are like extracted parameters of the chip. Here, this is not maybe it is a little bit of an analog twin, but you are not twinning a physical, thing. You are twinning a mathematical formula, and this mathematical formula, doesn't have capacitors, and actually that's a good thing, because if you put capacitors here, it will slow down the computation. There are going to be, by the way, because these are going to be physical resistors and physical currents, physical wires. They are going to have parasitic capacitance, but that's it's like any parasitic, you want to make that as small as possible. You don't want to introduce it, kind of artificially. It is going to be there. It is going to affect the speed of the computation, because, if you look just at this equation, this is infinitely fast, because, it's Ohm's law. So you apply a current, a voltage, you get a current, or you apply a current, you get a voltage, instantaneously, 0 time. But resistance does not introduce a delay. Only capacitance is introduced delay, only RC delays. If you apply it, again, there is no real resistance that infinitely fast, because real resistors do have capacitances. But, a resistor, a textbook resistance that, you use in your equation, there is no differential equation. This is Ohm's law. You apply a voltage, the current instantaneously has that value. There are no electrons. Yeah. The electrons, no, again, Ohm's law doesn't have anything to do with electrons. Again, Ohm's law is Ohm's law. No, it's infinitely fast. The math is infinitely fast, okay? So yeah, there is no, no ifs and buts. You are talking about a real circuit that has, resistors, capacitors, the voltage source itself has an output resistance. There are all these things, but again, you need to understand that pure math is pure math. You don't say, oh, there are 10, electrons and they kind of move slow, and no. Yeah, math is math. This equation doesn't have time in it, okay? So it's, Ohm's law doesn't have time. Okay, but yeah, that's not important. In reality, sure, there is delay, absolutely. Yeah, so, now, this circuit, the previous circuit is kind of, very, very ideal. Now, when you look at real circuits, you kind of, there is this concept of resistive RAM. And, to put things in perspective, the conventional memory types that, there are basically 3 conventional memory types that are, widely used. SRAM, which is typically used on chip, caches, 6-transistor SRAM, maybe a little bit more transistors once in a while, but then there is DRAM, main memory, 1T, 1C, 1 transistor for access, 1 capacitor for storing the bits. And then there's flash. And flash, it's let's say floating gate transistors where you store the, the information on that floating gate. And, you can have NOR flash or NAND flash, but basically NOR flash is not really used anymore because of density. So basically the density goes like this. This is the least dense, obviously, then the next, more dense, and, highest density. So, and, their usage modes reflect that. The least dense is used for relatively small memories, but, they are also, and there is a very clear, trade-off between size and performance. So these are the largest, but also the fastest. These are kind of medium size, also medium performance, and these are the, the most dense, but also the slowest by far. So these are used caches, these are used main memory, these are used storage. And, that reflects kind of these trade-offs. For storage, you really want, really large amounts. Doesn't matter that it's that slow. Main memory, you need large amounts. It's a little bit, slow, but it's fast enough. And then caches, you want them to be really fast. And then there are these, kind of emerging memory technologies that are trying to make inroads into these three that are dominating, the current landscape for memory. And there is most of these emerging, people that work in emerging memory technologies, they try to, push this idea of a universal memory. You'll hear this, universal memory. So what does universal memory mean? Well, universal memory is a memory that has characteristics of all these three, and that in principle could replace all three of them. So one characteristic that's, for storage is non-volatility. So basically you turn the power off, the information doesn't go away. For these two, it goes away. So that's if you are going to have a universal memory, it needs to be non-volatile, because if it's non-volatile, then it's not really universal. Then if it's going to be, universal, then it needs to be fast, because, you need to be able to use it as a cache. And if it's going to be universal, then it needs to be somewhat dense. Yeah. And, there are some, claims that magnetic RAM, for example, that use spintronic effects, might eventually become, a universal memory. What's interesting is, and, in our group, we've worked on spintronics for, more than, probably 15 years. We've done all kinds of things. What's interesting is that, all the attempts from there to kind of really make inroads here are very hard, because these things are a moving target. So, again, if you look back 10 years, the way spintronic memories, have evolved, they would have definitely overtaken that. But in the meanwhile, these guys are not sitting still, and actually it's kind of amazing, the advances that have been in the DRAM, with HBM and, and in NAND flash with 3D NAND. So there is no, it doesn't, no chance very soon that, these are going to really replace any of those. They do have applications. So MRAM, for example, and FERAM, because they are non-volatile and because they are denser and faster than flash, there are applications where you don't need very large amounts of storage, and you do want them to be a little bit faster. And, for example, in cars, black boxes for cars where, you want to store the last, few seconds before, an accident, a crash, so that you can, figure out what happened. That's where they use it. It needs to be non-volatile. It also, the other problem with flash is the limited endurance. So, you can only rewrite it a few, not that many times. So these new technologies, are better from that perspective. But what we are looking for now, we are looking for at them because we want to really use them to do these AI MAC operations. And this is another, a continuation on that table that, adds a few more categories that, are useful for AI. And again, the dream about this universal memory, you can see where that dream is, and we are very far from that dream still. So here we are, getting a little bit more details. So, instead of just Ohm's law, now we are going to have some actual, physical wires. So again, word lines, bit lines. You have these resistive RAM devices. These are called either crosspoint memories or crossbar memories because of the structure. Now, there are different technologies. So, and I'll try to move a little bit faster. There is this, one that's called phase change RAM. Are you old enough to have seen CD-ROMs in your lifetime? Okay, yeah. So, CD-ROM, and it's interesting that, let me make another parenthesis. It's the last day, so, we can have a little bit more free-form discussion. And, if you look at the, technologies that have had some success in these, non-volatile RAM world, they have built on existing advances from, very, well, not very different, but different fields. So the spintronics, the magnetic RAM technology has evolved on the, many years, decades of work on hard disk drives, magnetic hard disk drives. So we don't use those anymore. And now everything is flash, although maybe in some data centers, they still use magnetic, rotating. It's a very old kind of, obsolete concept. But there's been decades of work in making those, magnetic materials for the disks and for especially for the heads, actually, that read that information. And without that, we would not have the magnetic RAM memories because, all the materials, everything that's used there has been already invented by the hard disk drives people. Same thing with phase change. So, the reason we have phase change is really CD-ROMs and, and DVD-ROMs because, to write those, they use these phase change materials. The discs were coated with a transparent, coating, and with the laser, you basically heat up that material, and depending on how fast it cools down either as an amorphous. So if it cools down very fast, it becomes amorphous. And if it cools down slower, it becomes crystalline. And the properties, and these are the chalcogenides materials. This thing here, germanium, I don't know, GST. The optical properties are very different, and the optical property, between crystalline and amorphous. And the optical properties were used in CD-ROMs when you're reading the information. But it's interesting that the electrical properties are also different. And again, maybe it shouldn't be that surprising. So the resistance of the crystalline phase and the amorphous phase are different. And basically, that's how you can program zeros and ones in these devices. So, it's a two-terminal device. It's a resistor. And depending whether it's crystalline or amorphous, it's a one or a zero. Yeah.
Like this process is not infinitely fast, right? For just
No, it's not Ohm's law. Yeah.
Typical time, because this will limit how much fast you can write or read from the memory.
Yeah. No, it's pretty slow because it involves melting and solidifying. Yeah, I don't know, but it's definitely milliseconds maybe, or even slower, or tenths. Yeah, it's definitely slower than DRAM, and probably slower even than flash. But it does have much higher endurance. Still not infinite, but much higher than flash.
And do you know what is typically the temperature difference for this material to get converted from high resistance to?
Yeah, it's not the temperature; it's the temperature profile. So I think here, yeah, I don't know, but it's the temperature profile. Because you want to melt it, so that temperature is the same. So you first melt, that's no, but then it's if you cut, so basically you apply a current. So the way you get that temperature is really with Joule's law. So you basically pass a current, and exactly. So it just melts the material because but then when you cool it down, one option is to cool it down quickly. So you basically cut the current, and it cools down relatively quickly, whatever that means, and then it's amorphous. Or you can cool it down by not cutting the current, but ramping down the current. So that's going to be much slower, and then it crystallizes. Not perfect crystal, but it's kind of a polycrystalline. Yeah. Yeah, but the melt one, you don't call it a stage because that's just a temporary, it's a transient thing. So you only do that when you program. And you don't want to, again, this is not like an SRAM where you read, write. Again, the use of this is, like the weight stationary. So you program the weights and then you use it, and then maybe you reprogram the weights when you learn or you change the model. But so the melting is a state, but it's really not. It's just during write, so not during read. And it's just it's more like, I think they call it like a reset. So it's basically whatever was there before, whether it was crystalline or amorphous, you melt it down, you reset, and then you basically cool it down with two different profiles. Well, you need to reset if you want to rewrite. Yes, if you want to, you cannot go from a 1 to a 0 without going through the melting phase. Yeah, absolutely. Sure.
If I want to stack the memory on top of the processor, if the processor hits up, basically the leakage increases in the DRAM. So if the temperature increases by 10-15 degrees, does it still remain stable, or like?
Well, yes and no. So this is a second order thing. The real danger could be that the amorphous phase starts crystallizing. So it's So that has a, what's the term for that? It's, yeah, so basically any non-volatile memory has, several metrics. And, one is endurance, how many times, you can write. The other one is, yeah, it escapes me now, but it's basically this one. I mean, even flash, right? If you have a USB flash, don't put all your important information there and then keep it for 20 years, because 20 years later, it's gone. So it's kind of the same thing. So yeah, and I don't know what the numbers are here, but yes, any of these non-volatile memories are really not that non-volatile. So, it's, yeah. Yeah, I forgot what you call that. Yeah. So, yeah, so this brings us to something that, I have a love-hate relationship with, which is this concept of a memristor. And, I bet that there are a few students in the group, here that work on memristors. So memristor, this is, again, historical, was, proposed, many years ago. And it came kind of beautifully from the equations for flux, and basically there was this claim that there was a missing element in the resistor, capacitor, inductor, because you can have an equation that would make this whole graph symmetric, and it's a very beautiful concept, and a very beautiful discovery. It's kind of very catchy. And here are some, memristors, kind of, with there is this kind of butterfly curve that, is characteristics for memristors. And what happened was that, this was an old kind of long forgotten paper from Leon Chua. And, in 2008, about 20, a little bit less than 20. Well, they did this more than 20 years ago. So I should say that, I was part of this whole thing. And I told already some students, maybe again, it's a Friday, and we, seems like I have the, desire now to tell stories. But when I was an assistant professor, maybe this is going to be interesting to those of you that want to go to academia. I started as an assistant professor in 1996. And at the time, people were already predicting the end of Moore's law, but very seriously. Actually, a few years before, there were, professors that on the blackboard, at the time we used blackboards with chalk, they would prove, and this was in textbooks, that you prove that you cannot have a MOSFET with a channel length less than 1 micron. So 1 micron was this famous thing. If it's less than 1 micron, everything falls apart. And of course, by 96 we were past that, but there was still the very doom and gloom view of where the silicon technology is going, and basically, it's ending. And kind of simultaneously with that, there was this rediscovery I mentioned of Feynman's nano. There's a lot of room at the bottom, and Bill Clinton was president of the United States, and he had a science advisor. Turns out that he's Romanian, like me, kind of course American, but Mike Rocco. He's called Mr. Nano. But he convinced Bill Clinton at the time to invest something like $3 billion into nanoelectronics. because Moore's law was going to end and because silicon technologies were going to die and all that. So there was this, enthusiasm in the community for nanoelectronics, and DARPA had several programs with nanoelectronics. One of them that I was part of, and HP and Stan Williams were part of, was called Moltronics, molecular electronics. And the idea was to, there was someone that was asking me, will quantum computers replace digital computers? And I said no. But the idea of Moltronics was that molecules were going to replace transistors. So you are going to have circuits made with molecules. Molecules are kind of intrinsically nano size, so that's kind of a good thing. They are kind of fixed size, right? So a molecule has a size, there are not that many process variations. You cannot have a molecule plus half an atom or whatever. So there were some interesting, reasons for going in that direction. Stan Williams and the HP Labs group basically were working on molecular electronics two-terminal device. And, they were having, some success, and, it was interesting. But kind of what really made a difference and, a huge difference in terms of impact was that they figured out that this device, in some sense, was, in some sense, not very closely, but some sense equivalent to the Leon Chua memristor. And, when they published this kind of famous paper, I think it has, many thousands of citations by now, how we found the missing memristor. And this created a lot of buzz in the community. And even now, there are, in my opinion, way too many people working on these kind of circuits just because it's a cool concept and, it sounds interesting. It's created a whole thing. And it also has a relatively nice kind of theoretical way to think about it, although unfortunately, there is no device yet that really works this way. If someone figures out, this is a challenge for you. If you figure out a way to get a memristor, that works the way it's described here, I think that would be a real big advance. Because right now, memristors do not work this way. Whatever people call memristors, they do not work this way. But the idea with this is that you have a material that's, halfway doped and halfway not undoped. And by applying, a current in one direction or the other, you can kind of move this boundary between, highly doped and lightly doped. And by doing that, these two regions would have different resistivities. And, you have two resistors in series, and, the resistance of the two is kind of an average of the resistance of one. And, if it's all the way here, you can think it's 0. If it's all the way here, it's 1. And if it's somewhere in between, it's an analog value. So this would be really, really useful if there were devices that really work this way. And it's a very beautiful kind of conceptual thing. And here are some, models, simulators, showing how these memristors work. There is this butterfly curve, a pinch hysteresis loop. Yeah.
Why I'm so excited about this technology? Can we have these amorphous, like these chalcogenides and all integrated with the silicon, or like are foundries capable enough to do that? Or
yeah, they are. Yeah. So I think so here actually this is exactly addressing your question. So the very nice thing about many of these technologies is that they are low temperature processes. So many silicon, many processes in silicon are, high temperature, everything that has to do with semiconductors and all that. And that's why, chip fabrication is kind of divided into these two, front end and back end. So front end is basically the silicon wafer, very high temperatures, and then the back end where you have metals, evaporate at, the temperatures for the front end. So once you have the back end, you cannot really put transistors anymore. So that's why it's hard to have 3D, what's called monolithic 3D. So in order to have monolithic 3D where, it's not just two wafers that you sandwich together, you need a low temperature process for active devices that then can work with the back end, with the wires. And yes, these materials are like that. So, and this is, and there are some, So this is actually an example, and again, it's kind of interesting that unfortunately it failed. I was a big believer in this technology. So this is a technology that basically two major, US companies worked on, Micron and Intel together. It was developed by, kind of as a joint program. It was called 3D XPoint, the technology. Each of the two companies had different kind of marketing terms. So Intel was calling it Optane. And it was relatively wonderful. So, so here is how Optane looked like. Again, very similar to what we've seen until now, except that they were envisioning a 3D. So, multiple layers, not just one layer. And they figured out, one issue with these resistive RAM arrays devices is that many times you need, one transistor. So it's like 1T, 1R in order to do the access, but they figured out a way instead of a transistor to have basically a diode. And that diode was, some kind of, and I think it was like, we still don't know what they were doing, frankly. They never really gave away but, it was a sandwich of different materials. And, one part, and let's say the orange part, I don't know whether it's orange or green, but one part was the selector. Oh yeah, actually they say here. So this is the selector, which is, you can think of it like a diode. And then the other one was the memory cell, which can be basically 0 or 1. So, it doesn't have that memristor thing where you have a continuous value. But, it was a wonderful, technology, very good density. So, for memory, there is this concept of F squared. F squared is the, the unit. F is basically the kind of the minimum feature size. F comes from feature. And then basically you can express any memory if you look at the area of the cell as a multiple of F squared. And kind of the smallest area that you can have is 4F squared, because you basically need the wires. You need vertical wires for bit lines and horizontal wires for word lines. And that's the maximum density that you can have, as long, if you are going to have a two-dimensional array. Because basically the memory doesn't take any extra area. It's right at the, it's under the wires. It's basically at the cross-section area. And you can stack them like this. But what killed it is really the market. So this was denser than DRAM, but less dense than flash, okay? And it was, again, denser than DRAM, but slower than DRAM. So it fell in a weird kind of place in the, in the memory hierarchy. Because if you have something in between two memories, one that's fast and large and one that's slow and small, it's not clear that you need something in the middle, because you can use these two to kind of do what the one in the middle does by optimizing where the data is in those two. And kind of that's what killed this technology, unfortunately, because I really liked this technology, and I think but yeah, it was, and it was one of the unlucky things for Intel, I guess, because, but yeah, basically the advances in flash with 3D NAND really killed this, because, 3D NAND, again, if you follow 3D NAND, from one generation to the next, the increase in the number of layers is not linear, It's basically, it's an exponential. So, it kind of doubles, or if it doesn't double, it's 1.5 times larger. So, by now there are several hundred layers in a 3D NAND. The 3D with this method would be linear, because every new layer you kind of add, it's an extra step. So, yeah, it's again, the progress in 3D NAND is what, okay, we are really behind. So, okay, we are finally to where I was trying to get. So we are back here. That's what we want to do. And now a little bit of terminology. And again, this terminology is a mess for people that work in processing in memory, which we are. The terminology is a mess. There is no agreement whatsoever on how to call these things. I mean, it's all over the place. In memory compute, IMC, compute in memory, CIM, processing with memory, it's all over the place. But again, this is kind of one way to break the memory wall. So this is basically the von Neumann. This is what I call near memory, because it's still von Neumann, but the wall is just much smaller because you bring things there. But then this is some people call this processing with memory, because you are really doing the process. And again, this is about SRAM. Here probably you should replace with any memory, because this discussion is true about RRAM and any other things. Say that again. So what? So yeah, I mean, if you are confused, I'm not surprised. But so what's the question? These are just examples of what people call processing in memory. And again, it's not exhaustive, and it's not coherent, and it's not consistent. That's all I can say. But yeah, these are possibilities, and there are many others. I mean, like I said, a first variable, is this SRAM? Is it RRAM? Is it phase change memory? Is it MRAM? So, whatever this memory is, it's one dimension. But the other dimension is how you do the computation. Do you do the computation in digital? Do you do it in analog? And there are many others, yeah. Yeah, so I'm not going to read this. Some things that, so the benefits are pretty clear. We kind of discussed about this. And here it even talks about the capacitance. So kind of intrinsic, yes, there is capacitance, but intrinsically it's small. There are these challenges. We already talked about non-idealities, which is the precision thing, and everything else. And another one that's kind of unfortunate is that whenever you have one of these analog blocks, and that was actually maybe a problem with the Optane as well, is that it needs to be part of a digital computer. So you need to make it, the in-memory compute, it needs to be compatible with the digital computer. It needs to exchange data back and forth, all these things. So, for example, in the worst case, for every Mac operation, you need a digital to analog compute conversion. So you need to take, you have your inputs in some digital format. You need to do a D2A conversion, apply the voltage, read the current at the end, and then do an A to D conversion. And that's, quite expensive. And if you do it for every analog computation, it kind of defeats the purpose of the analog computation. So again, if you are going to do something like this, it's better if you can keep the data in analog format for, some time before you need to convert it back. Or you can have a purely analog solution where you don't go back to digital. Sure.
Like IHC.
Yeah.
It's complex. Like, can we achieve that much complexity like digital computing in IMC?
Okay, so yeah. No, okay, but yeah, maybe go ahead. Yeah.
So still, I can see like minimal kind of computation is possible as of now, but how much complex computation can be doable?
Well, so the question, so if the question is if you do everything just in memory computing and you don't have anything around, then definitely there are the limitations that we talked about, I think, yesterday, where you are trying to map the whole, model to, and then the wires, and would be, 100 centimeters square or whatever. But that's not what people are doing. So what they are doing, they are using these in-memory compute engines as a as an accelerator. And at that point, it's a trade-off. You don't need to do everything in there. You can still have digital computations, whatever. So, and it's like, like hardware, software co-design. In this case, is like, in-memory digital co-design. So you have to figure out what you do in digital, what you do in the IMC. And if what you do in the IMC is faster, smaller, lower power than what you do in digital, then you do. So I think that, yeah, so I don't think there are actually people that, argue that, yeah, we should do everything in IMC. So, yeah. Yeah, so this is basically, the kind of the simplistic, I should say, way of doing things, and, there are, these are research, but this is a paper that has a lot of citations and a lot of impact, Isaac. It was at ISCA 2016, which is the most, the major computer architecture conference. But you see, it's, some more about, I would let you, read this paper if you are interested. I'm not going to go into details here. Another paper that is doing something similar, also at ISCA 2016. I'm not sure what that means. Means that it doesn't change for them, but no, I mean it, Can you see this slide on the Zoom? Yeah, so okay, maybe it's on their end. So yeah, so here we can see it. Again, some, and you see it's like this thing. So you still have a CPU and, and it communicates with this accelerator. And this is an important thing. That's why I, circled it in red. If you look at GPUs, right? So GPUs were really successful because at the beginning, a computer would have a GPU already inside, and now you just repurpose it for, doing scientific computations. So you did not ask the user, the customer, to pay something extra for, your accelerator. For processing in memory, and there's been already a few products that failed as products. There have been products that were processing in memory where that, device could only function as a processing in memory device and could not function as memory. So basically, you were asked to buy a device that you are only going to use when you use it as an accelerator. And, that's really not a good, proposition to a customer because, you ask them to buy something extra. So this is a very important concept for processing in memory, I think, to be successful. It also needs to be main memory. If I'm not using it to do computation, I should be able to store and use it as memory and only, use it as, as an accelerator when I need to.
So when the people do research on the preamp, do they take into account the power consumptions of the ADC and the DAC? Because as I increase if I want to make the multiplications much faster, the voltage waveform has to run at a gigahertz frequency. The weight stationary will make sure that the resistors will remain constant. That means the current waveform itself is changing with the gigahertz rate. Now we are trying to sample that, so we need a multi-gigahertz sampling rate ADC, which will consume a lot of power.
Yeah, you are basically making the case of what I said, that because of the A to Ds and D to As, these solutions kind of lose all the benefit. If you are asking if the people that write the paper, if they do that, well, maybe they will try not to do that so that their solution doesn't look bad and, they can get their paper published. But yeah, they should do that, yes. Yeah, if you're asking if you should, you should, yes. There are some noise, discussions. I'm going to move about, this. But, here is an analysis with the noise resilience for different, models. We've seen ResNet and VGG and MobileNet. Once you put noise into the picture, the accuracy for some models stays, reasonable, but for some models drops like a rock. So, this is another example of co-design where, you want to co-design your model with, your actual device, and again, not, kind of hide under the rug the non-idealities. I'm not sure that I'm not sure that, you can figure out why some of these are so much worse than others. I'm not sure. Maybe if you read the paper, and you can notice here that this is from the same author as the IRIS paper, Vivian Z. But it's an important, again, it's kind of like the discussion with A to Ds. It's not enough to just look at the ideal case. You need to look at the real case.
Processing in memory assumes basically a finite precision, right? If I do floating point, all the operation on using floating point 32, and now, you had just mentioned in few slides back that the accuracy that we get usually from these processing in memory kind of computation, it is just limited to 3 to 4 bits. So that makes sense why the accuracy can drop, but it should have dropped for all of them. Some models seems to be very resilient to that.
No, well, So again, I'm not sure why you say it should drop the same for, no. I mean, no. I mean, no. But yeah, let me explain what I mean. So there are, I mean, it's like weather, right? So there are some weather patterns that are, stable, and there are some weather patterns that are unstable. So it's a little bit like that. So some of these models are not stable to, to changes, and some are, more stable. So yeah, I mean, that's basically what this analysis says. And then, here basically, they are doing some, more discussion on this noise. And, once you have this, you get maybe, there's still a big difference, but, you can decide which one you like more. I'm not sure. Read this paper. Yeah. Again, it also depends on the depth. You see ResNet 18, 50, and 152. And the filter size, 3 by 3, 7. So I think the point of this paper is not necessarily to learn something specific, but to learn that if you are going to be a company that's trying to make a product that uses something like this, you should look beyond just, a theoretical analysis and actually try to understand the limitation of the technology and, do something about it. And, and the interesting thing is that the results can be quite, dramatically different, much more so than you would think from a theoretical analysis. And here is the precision, the number of bits. I mean, yeah, some of them, clearly are not feasible. For example, this one requires 8 bits of precision. You are not going to get that. So you really need to be, in these kind of 2 to 4, and basically be maybe, yeah. So, these two are kind of the best. And, if you can be around 5 bits of precision, you are going to do well. That's the bottom line. Yeah, so I think with this, we are going to wrap up finally. This was a long lecture. So there is one company that, and I think I already mentioned it, but, I'm going to get a little bit into more details here, that, made it into commercial world. They sold product, they sell product, so they were somewhat viable. They went through a bankruptcy, but they've been rescued by, by the US government, basically, I think by the Department of Defense. So again, they are basically, so I'm not going to spend time, they are still doing this, Mac operation. They basically do exactly what we discussed about. The only thing that's, and this is from their paper, so it's just an analysis, and they consider 1 million weights and things like that. They are basically targeting these multi-million weight applications at the edge. So what's unique about them is that they use a floating gate device instead of some of these other devices. So that has advantages and disadvantages. The main advantage is that it's basically very compatible with with a conventional CMOS process. So there is no, for example, magnetic materials are very tricky for if you go back maybe 10, 20 years ago, the foundry people would not let you get into the clean room with anything that's magnetic. Nowadays, they figured out some way to do magnetic, but again, it's a very separate operation because, you know, magnetic materials are very tricky for fabs. But, you know, floating gate is purely, you know, purely, you know, silicon compatible. And, you know, they have that kind of slightly more complicated 2D array. You know, there are basically 2 vertical wires and 1 horizontal instead of 1 and 1. And again, I'm not going to, this was for my students. I hope everyone here knows, who doesn't know how a floating gate device works like? And, you know, it's not, everyone knows how a floating gate device works like? Yes, no? Okay, yes. Okay, so I'm not going, they do. Yeah. Yeah. Okay. Yeah, so I'm going to move on. Yeah, so basically this is, again, their device, nothing new there. They have DACs, they have ADCs, and basically that's why they went bankrupt once because of those DACs and ADCs. You know, you know, they have this, you know, processing unit that they call the Mythic IPO. You know, they have a RISC-V to kind of control the process. They have, you know, an SRAM for the RISC-V. They have a, you know, and here is to answer the question from Professor Ambika. So they have a SIMD here that, you know, does computation when needed. They have a router, but then, you know, when they do the input-output activations, they use the flash. So again, this is from their own, you know, slides. But yeah, they envisioned that you would have multiple models simultaneously in their flash, and you would basically do, you know, one model. So you, again, this is to avoid reprogramming the array. So, you know, if you do object tracking, you'd use this model. If you use, you know, something with the camera, like, I'm not sure what enhancement means, maybe contrast, use this, maybe, and scene segmentation here. Yeah, so kind of 50 million weights, you know, again, in the future generation, you know, 250 million weights. And here is for, you know, they are comparing themselves against, and of course, they are comparing in a way that makes them look good. But yeah, they are comparing against, this would be enterprise, basically means, you know, what, you know, the large ones. I'm not sure what this no DRAM means. I'm not sure what that would be, but basically if you are on the edge with DRAM, edge with the, and, you know, they claim, you know, an order of magnitude better energy efficiency than, you know, than, well, even than this one. I'm not sure why this one would be more than that, to be honest. That's kind of bizarre to me, but yeah. Yeah, so that's kind of the Mythic thing. So Mythic went out of business, are back in business, and they are an example of a resistive RAM kind of company. Okay, with this, I would say let's take what? Yeah, tea break, yeah. And then we'll be back at 11, right? 11:10, okay. Okay, thank you, guys.